So we discussed the basic rock and fluid properties you need for simulation in the previous video. And now we move on to additional data that you may need depending on the process you're modeling. So here, if you're modeling gas oil displacement and you have gas saturation always increasing, meaning drainage or imbibition. If gas saturation is increasing, is that a drainage process or an imbibition process? What is an imbibition process? Imbibition is just increase in the saturation of the wetting phase. So if water is the wetting phase and water saturation is increasing, then that is an imbibition process. If the water saturation instead is decreasing, then you're looking at a drainage process. So here, because the gas is a non-wetting phase typically, then you're looking at a drainage process, because for the gas saturation to be increasing, the wetting phase saturation has to be decreasing, and a decrease in the wetting phase saturation is a drainage process, and that's why you see drainage show up here. So of course you need the rock permeability, which is a measure of the ease of flow through the rock. Then if you have multiple phases, here we're talking about gas oil displacement, right? So you need gas and oil relative permeability, KRG, KRO, and they're usually plotted against saturation, right? If you plot it against saturation, it typically looks like this, depending on the properties of the rock. You also need the rock compressibility, CF. Then more fluid properties that you need for a gas oil displacement process, a drainage process. You need solution gas oil ratio, right? Is the gas in solution, meaning the gas dissolved in the oil, plotted against pressure, and typically it looks like this. Then you need formation volume factor as a function of pressure. So I'm putting it here, I'm plotting it, but the simulator needs the parameters that it's going to use to construct this function. So basically it needs RS as a function of pressure. You can write it as RS this way, right? Of pressure. Same with all these other guys. This is formation volume factors, which I discussed in the previous video. Same deal for oil and for gas. For gas, you can get it straight up from equation of state. How? Because you know it's Vg at reservoir conditions divided by Vg at standard conditions, and you already know what standard conditions is. So plug in the value of standard conditions into PV equals ZnRT. So T will be 60 Fahrenheit and P will be 14.6, and that will give you VSC, volume at standard conditions. Then instead of standard conditions, plug in this PSC, plug in pressure at reservoir conditions and temperature at reservoir conditions, and you will get what the volume should be at reservoir conditions. Then do the ratio of the two together, you get your BG, because BG is this. Then you need the equation for viscosity as a function of pressure, right? You need it for oil, for gas. The simulator needs it. And guess what? The equation is already programmed into the simulator, but the equation needs some parameters. For instance, this is a common correlation for viscosities. It's a viscosity at a reference condition. I can put it as mu r times exponents of some c as a function of C multiplied by P minus P at a reference. So this pressure in the reservoir. Let's use 0 as a reference. So this equation is implemented in the simulator, but you need to provide the inputs. This this, and this. So that's the case for most of these functions we are writing here. It's implemented in the simulator, but it needs input from the user. And these are some of those inputs that you will need to calculate this. I showed those in the previous video. What if you have an imbibition process? Water saturation increases, right? Because water is the wetting phase. So increase in the wetting phase saturation is called imbibition. So water oil displacement process, but water saturation is always increasing. So it's all imbibition. And it's important because of what is known as hysteresis. So we have capillary pressure hysteresis. If this is your capillary pressure function, pressure as a function of SW and PC, capillary pressure as a function of SW. So this is SW increasing this way, right? So if we're going down this way, we have imbibition. Then if we get down here and we want to go back up, meaning we want to start decreasing water saturation, well, it's going to trace a different curve. So it's not going to go along the direction of this, and that's the hysteresis, because it's path dependent. It's not reversible. It traces a different path, and that is drainage. So you will need the equation for imbibition in this case, different function for that. Whereas here, when we had gas oil system, the capillary pressure you need will be the one for drainage. Good. So for imbibition, we actually use the red one. I already discussed this within the context of oil and gas, same deal. Formation volume factor for water and viscosity for water. Provide the equation. The equations are provided in the simulator. You just need to provide the inputs you'll need. So mu W at reference conditions, the reference pressure, and what else? And the C, compressibility, that's going to be used in that function. Same for this. This will be a function of the reference pressure, the fluid compressibility, and what else? And BW at a reference condition. And the BW, so this is for RS, right? This sketch here. The BW looks similar, but it's not a straight line after it hits the bubble point. So this is the bubble point pressure. That's pressure increasing. It curls down a little bit. And that's how BO looks like. And this is how RS, solution gas oil ratio, looks. More data needed if you're describing a system where oil is invading a gas cap and you have interstitial water saturation, or an aquifer where there is no gas, so single phase water. Well, these are the additional parameters you need, and you get the idea. You always need relative permeability and capillary pressure whenever you have multiple phases flowing. If it's single phase, you don't have capillary pressure, because remember, capillary pressure is a difference between two different pressures in two different phases, and you have only one phase, so it doesn't exist. There is no concept of relative permeability, meaning permeability to one fluid in the presence of another fluid when it's single phase. And that's the main difference between single phase and multi-phase flow. In multi-phase flow, you have relative permeability and capillary pressure. And those are the relative permeabilities and capillary pressure as a function of saturation. And you need to account for hysteresis. So depending on the direction of your increase in water saturation, you create the function, or you provide the input parameters that describe the process you are interested in. If it's a three-phase flow, then you will have two different relative permeabilities. Actually, you have three relative permeabilities to oil, in the presence of the other phases to gas, and to water. All of them are plotted against saturation. Typically, the one for oil and water are plotted together. So relative permeability to oil will be this. This will be relative permeability to water, and you plot those against water saturation. Then you plot one against gas saturation for KRG. This will be KRO, this will be KRW. And we'll talk about those some more. I mean, these are standard petrophysics stuff. And I'm going to defer this discussion to the next video.